Hey guys, today we are going to do 5.4, which is about exponential growth and decay. I'm going to try to go fast because there's kind of a lot of stuff to cover. So I don't want to go over like I did last time. So Common Core State Standard, FLE1. Right, FLE1, recognize situations in which a quantity grows or decays by a constant percentage rate. Some vocab, exponential growth, decay, growth factor, decay factor, and compound interest, which all of you will use at some point in your lives. We're going to jump over this one because for the sake of time. Okay, so this is what an exponential function looks like. We've went over this already. If it's going up like this, how it's increasing quickly like that, that's going to be exponential growth, okay, because it's growing. Exponential growth can be modeled by the function y equals a times b to the x. We've talked about that already. But I'm going to give you a different formula for exponential growth because I think it's a little bit more useful. So I want you to make sure you write this down and have it in your notes somewhere. But it's going to be y equals a. Again, that's still your initial value. But instead of b, I'm going to say parentheses 1 plus r to the x. Okay, and r is going to be your percentage rate that it's growing. Okay, so this r is percentage rate, percentage growth rate. Okay, and a is still your initial value. Okay, so please write that down, have it in your notes somewhere. So basically we're just replacing b with 1 plus r. And I will show you why I'm doing that in the next slide. Okay, so this one says, since 2005, the amount of money spent at restaurants has increased about 7% each year. Okay, so this is your percentage rate here. In 2005, about $360 billion was spent at restaurants. If the trend continues, about how much will be spent at the restaurant in 2015. Okay, so really, you need to write your equation first. For the equation, the 2005 doesn't matter. That's just when it started. Okay, so we're going to start with, well, let me write down the formula. Y equals a times 1 plus r to the x. Okay, in this case, a is going to be our initial value, which is 360 billion. I'm just going to do 360. I'm not going to put all those zeros, and our units will be in billions. And then rate is going to be the 7%. But when you put your 7%, I'm not going to do 1 plus 7. You have to change that to a decimal. So remember, to change 7% to a decimal, we just move the decimal back twice. So that's going to be 0.07. So 1 plus 0.07 to the x. That just becomes 360, 1.07 to the x power. Okay, the reason that we're doing the 1 plus is because now this is really like 107% because you always start with 100% of your initial value. So we have 100% plus the 7% each year. So that's why it's 1.07 and not just 0.07. Okay, because it's growing. So 107% or 1.07. And then it says, so this is the first part, this is our equation. If the trend continues, how much will this be spent in 2015? So x, this is going to be time. So how much time has gone by? And that from 2005 to 2015, that was 10 years. So clearly this is a little outdated because 2015 is already passed. But we just plug in 10 there. So we get y equals 360, 1.07 to the 10. Okay, so that you're going to have to type into your calculator because it's very hard to do exponents when it's a decimal in your head. So we get 706, 708.17 billion dollars. All right, so you guys go ahead and try this one, and I'll do it on here, and then we can compare our answers together. Ready, break. Pause in 3, 2, 1. All right, so the 285 is your initial value. That's how many people had a cell phone in 1985. and it grows at 75% each year, so that's where I put this 0.75 here. And then in 1994, that's 9 years later, so this 9 goes right here. And if you type that into a calculator, you get about 43,872. So clearly not very many people had cell phones in 1985, but in 1994, lots of people had cell phones. 43,872 of them.
All junior high students, please report to your B1 for roll and lunch count. All junior high students, please report to your B1
as you can see,
for roll and lunch
with
count.
exponential functions, they grow very fast. In just 9 years, it's went from 285 to almost 44,000. Alrighty, next thing we're talking about is compound interest, which again I said that you all will use because at some point you're going to have to get either a car loan or a house loan or a student loan. But what compound interest is when you borrow money from the bank and you have to pay, when you pay that back, you're not just paying back how much you borrowed, you're paying back interest. So basically the amount it costs for them to loan you money. Or if you put money into a savings account, they pay you interest. Okay, it's generally a lot less than the interest that you would pay, but you know, it's still compound interest. And compound interest grows exponentially. So that's why it's in this exponential functions unit. So, important formula here is the compound interest formula. It's very similar to the growth rate or the exponential growth formula. There's just different letters. So A is going to be your balance. That's how much money you either have in your account or how much money you owe. Okay, P is your principal. That's your initial amount again. We just call it principal. We're talking about money. R is your annual interest rate. So again, your percentage rate expressed as a decimal. Don't forget that. Now N, this is the new one. N is the number of times the interest is compounded per year. So if it says compounded annually, that's only one time per year. But if it says compounded monthly, that means it's compounding 12 times per year. So that'd be 12 for N. And then T, again, is just time in years. So how many years? Okay, so write this formula down. You need to know that. Okay, and then we will look at this example. So it says, suppose your friend was born, when your friend was born, their parents deposited $2,000 into an account paying 4.5% interest compounded quarterly. Okay, so they deposited $2,000, 4.5% interest compounded quarterly, and what will the balance be after 18 years? So if we write the formula first, your variables are going to be the A and then the T. Okay, so let me just rewrite the formula. A equals P principal times 1 plus R over N to the NT. And now we just need to plug in our numbers. So 2,000 is going to be our principal. That's how much you start with. So that's P. So we get A equals 2,000, 1 plus your interest rate, 4.5%, but I got to change that to a decimal. So move it back twice. So 0.045 over N. And N is going to be how many times it's compounded. So if it's quarterly, that means 4 times per year. So over 4. And then this is the same N, so these are the same. So I put 4 times T here. And in this case, T is going to be 18 years. So then I can just plug in 18 for T. Okay, so A equals 2,000. Make sure you're using parentheses when you do this. That's going to be 0.01125 to the 4 times 18, which is 72. Okay, then just put that in your calculator. And what do we get? 2000, 1.01125 to the 72. So that comes out to be 4,475.53. So because you're talking about money, you're always getting around to the nearest cent or the nearest hundredths place. Okay, so in 18 years, this is if you don't put any money in or take any money out. After 18 years, there will be $4,475.53 in your account. Also assuming the interest rate doesn't change. And that's compound interest. Okay, so this one is the same question. It just says it's compounded monthly instead of quarterly. So why don't you go ahead and write the equation and see how that changes the outcome. Okay, you can pause this in 3, 2, 1, pause. Okay, so this one you just change your n here. Last time it was 4, now we're changing it to 12. So these two numbers change here. They were 4, now they're going to become 12 because it's compounded monthly. And when you put that into your calculator, it comes out with 4,489 and 1 cent. Okay, versus this was when it was compounded quarterly. Okay, so it's a little bit, you get a little bit more money when it's compounded monthly than when it was compounded quarterly. I mean, granted, $14 over 18 years is not much, but this gives you the idea that the more times it's compounded per year, the better off you're going to be, so the more money you'll be getting. Okay, so even if it was compounded daily, that would go up a little bit more. Not a whole lot, but, you know, a little bit. Okay, so compound interest, friends. Okay, and then we have exponential decay. Okay, so very similar to exponential growth, but you can see that your function is now going down like this. So it's getting smaller. So we call that exponential decay. And again, you can use the same formula that we did before. I'm going to give you a new one though. So it's going to be y equals a, which is your initial value. And then remember the last one was 1 plus r for exponential growth. This one's going to be 1 minus r to the x, okay, because it's getting smaller. So 1 subtract r. And this r again is your percentage rate. And a is your initial value. Okay, so that's going to be your exponential decay formula. So please have that in your notes as well. And let's look at this here. This says the kilopascal unit, or is a unit of measurement for atmospheric pressure. Atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases by 11.5%. What is the approximate pressure at an altitude of 3,000? So we need to write the formula first. So we do, let me just rewrite the formula. Y equals a 1 minus r, because it's decreasing, to the x. That's an x, most definitely an x. Okay, and we're starting at our initial value, which is sea level, 101 kilopascals. 1 minus 11%, again, needs to be a decimal, so 0.115 to the x, and in this case, our x is going to be, well, we're going up 3,000, but 3,000 is not going to be the x because we're going by every 1,000 meters. So I'm going to plug in 3, because there's 3 sets of 1,000 there. Okay, so I get y equals 101. That's going to be 1 minus 0.115. Oh, 0.885 to the third. And that comes out to be 70. So about 70 kilopascals at 3,000 meters. Okay, on we go. This one is the same problem, except instead of 3,000, it's 5,000. So basically, you just change your x to 5. So I'm not going to do that one. You guys can go ahead and try it, though. I think that one's on your quiz. This is why do you subtract the percent from 1 and to find the decay factor. So again, you're starting with 100%, which is your 1, but it's going down 11.5%. So 100% minus 11.5 gives you 88.5%. So that's why you're subtracting 1, because it's decaying. Okay, and then this brings us to writing exponential functions, which is kind of a weird thing to put in this unit, but it's not too bad. Okay, so remember your exponential function. If it's not growth or decay, it's not a percentage rate. You can just think of it as y equals a times b to the x. So a is going to be your initial value again. That's really hard to read, sorry. B is the growth rate. or what you're multiplying by or dividing by. Oops, growth rate. Okay, your initial value is your y-intercept, so that's always going to be when x is 0. So this is your a, that's your initial value. And then you need to figure out how much you're multiplying by each time, and that's going to be your b. So we go from 1 to 3 to 9 to 27, so all these are multiplying by 3. Okay, and this is going to be your b value. So we just plug it in. So we get y equals a, which is going to be 9 here, because when x is 0, y is 9, times b, which is 3, to the x. Okay, and that's your formula. That's your equation, your function. Okay, I need to scroll down here. So y equals 9 times 30x. 9 is your y-intercept. 3 is the growth rate. And it's growing, so it's going to be a 3, not a 1/3. This one is decaying. It's decreasing. So that tells us that our b is going to be a fraction. So let me just rewrite it up here. Y equals a times b to the x. Our y-intercept is where it crosses the y-axis here. So that's going to be right here at 4. Okay, so this is a. And then the next point, if you go over 1, we go from 4 to 2. So in this case, to get from 4 to 2, we divided by 2, which is the same thing as multiplying by 1/2. Okay, we took half of that. So that's going to be our b value. So we get y equals a is 4 times b, which is 1/2, to the x. Okay. So if it's going down, decreasing like this, it should be a fraction in here, smaller than 1. That's why it's 1/2. Okie dokie. Okay, you can go ahead and try this one. Okay, I'll put it on pause, and then we will reconvene shortly. 3, 2, 1, pause. Welcome back. Alright, so this one starts at 8, that's your y-intercept, and then you can see you're dividing by 4, which is the same thing as multiplying by 1/4. That's why we get 1/4 here. Okay, so this one is decay, it's getting smaller. This one here's growth, so it's going to be a whole number. So we start at 2, that's our y-intercept here, and then from 2, the next point goes up to 6. So we multiply by 3. So we get 2 times 3 to the x. Alright, not too crazy. And that is all I have for now. I need to get going to the science fair so I can judge all of you. But thanks for watching. Stay tuned for my next video. It's going to be a good one. Maybe. Okay, bye.